Hello, folks. So welcome to section 6.3. In this section, we're going to talk about performing operations with functions and function composition. Our goal is to just be able to do these two things. To start off, operations with functions. Operations, pretty simple. We're going to add them, subtract them, multiplying, and then we're going to divide them. It says let f and g be any two functions. We can actually form a new function h, and it can be defined by performing any of our four basic operations. So when we add our functions together, you might see here we have h of x could be f of x plus g of x. It's just as simple as adding our polynomials together like we did in chapter 5. So up here, if we have f of x being 3x and g of x being x plus 3, if we want to find the new function h of x by adding f of x and g of x together, that's the same thing as taking 3x plus x plus 3. So we get 3x plus 1x plus 3 or 4x plus 3. And that's just as simple as it is for addition. It's really not too bad. Subtraction, the most common error I'll see with subtraction comes in the signs. Here, if we subtract the two functions, f of x and g of x, what you'll see is here's our f of x, and here's our g of x. And when we subtract them, remember you want to make sure you distribute that subtraction sign into that quantity. So it's actually like we're doing 3x minus x minus 3. And when I simplify that by combining my like terms, 3x take away x gives us 2x, and then minus 3 comes along for the ride. So you just want to be mindful of the idea that when we subtract, we add the opposite of that second quantity, and that's the most common error I'll see. Just something to keep in mind when you come into class the next time. Our warm-up is going to be to have you pull out some fun facts or processes that you learned about addition and subtraction, and then multiplication and division. So you kind of want to keep in mind like the how process as I go through each one. And then multiplication. Sometimes we FOIL, sometimes we use the distributive property, but here if we were asked to multiply f of x and g of x, that's just as simple as doing, in this case, 3x times the quantity of x plus 3, and that's our distributive property there. You'll see that we distributed the 3x to the x and the 3x to the 3, so we get 3x squared plus 9x. I should also comment, too, if at any point in time the video goes too quickly for you or you didn't get to write something down, use your space bar or your pause button on your viewer, and that'll help. You can also rewind, if you need to see something explained again. It's kind of nice that way. So make sure you use those options as you watch the video. Division is just setting up a ratio of your two functions. So in this case, if we wanted to define the new function h of x as a quotient of f of x and g of x, it's just as simple as putting, for now, f of x over g of x. So we have 3x over x plus 3. You want to try to reduce this function if possible. We spent a good amount of time during our last lesson identifying domain and range, and you're going to see that that word keeps coming up in pretty much every section for the rest of chapter 6. That's why we had to spend the amount of time that we did it in our last lesson. What you should notice is that when you want to find the domain of your composite function here, or of your function that's sort of combined, made up of two functions, the domain of that new function has to consist of values in the domains of both f and g, so both of your original functions. You could always, if you're worried about it, I'm going to show you how to do it here in a little bit. If you were super worried about it, you could always throw it into your graphing calculator and check the graph and identify the domain that way. One last thing, whenever you're making a quotient of two functions, your domain can't include values that would make your denominator 0, or, in other words, g of x, that bottom function, isn't allowed to be 0. And ultimately, yeah, that's because we can't divide by 0. Nobody can. So for instance, in this guy here, x plus 3, that was our g of x on the bottom. X would not allowed to be, it could not equal negative 3, because that would make 0. in the bottom of that fraction, so we would have to exclude -3 from that function's domain. So that's just a real quick run through on how you do your 4 operations with fractions. Just for some additional examples, oops, a lot of information there. I wanted to maybe make them a little bit more challenging, like give some rational exponents, since this is chapter 6. If I want to find g of x, find h of x when f of x were 4x to the 1/2 and g of x were -9x to the 1/2, I could add or subtract those two functions. So I'll show you that out here. If I want to add f of x and g of x together, what you would see is I would take 4x to the 1/2 and add -9x to the 1/2 to it, and just combine your like terms. You get -5x to the 1/2, which you folks know is the same as -5 times the square root of x. And then if I wanted to find the difference between those two functions, I would do 4x to the 1/2 minus a -9x to the 1/2, and you'd actually get 13x to the 1/2. Remember, you folks know that that is the same as 13 times the square root of x. So if we want to find the domain of that function in part A, because it does say our domain there, you could use your calculator to think about that, for sure. So you go to your y equals screen in your calculator, and we would type in our function. So we have -5 times the square root of x. It's going to graph it in y too, that's okay. So you'll see there that you get this graph. I'm going to screen capture it so we can talk about it a little bit. So we get this graph for our function here, y equals -5x to the 1/2. And we're asked to, in the previous problem, identify its domain. You might recall that this is the same as y equals 5 times the square root of x. And we know that we can't take the square root of a negative number, ever. And this graph definitely verifies that. We see its first point is at the origin, and then kind of comes down and continues on like that. So if we were thinking back to how we define domain as the space that the graph takes up on the x-axis, this function starts at 0, which is actually a point on the graph, and then it does head towards positive infinity. So that's the domain there. And honestly, it's actually the domain for both, because both are square root functions. So yeah, in one more place you could look to confirm the domain as starting at 0 and heading towards positive infinity. You go back to your calculator and you press the table. You'll see that for values that are smaller than 0, we don't have any values that exist. -3 is an error, -2 is an error, -1 is an arrow. The first values we get are 0, and then it does take off from there. Like, it just keeps going. So we get values for everything after 0. You could scroll ahead and see that for sure. So that's kind of another place you could look to verify the domain of your function. And then one more here. In example 2, they asked us to divide these functions, and I like this problem because it makes you review a little bit about your properties of exponents. So if I have f of x equals 6x and g of x equals x to the 3/4, you'll see if I multiply these together, essentially I would be taking 6x times x to the 3/4. In the next step over there, you'll see I used my sort of associative property of multiplication to regroup and put my bases together. And then 1 plus 3/4, that's 1 3/4, or 7/4. And then for part B there, we have a ratio of our two functions. You'll see I wrote 6x as 6x to the 4/4, because 4/4, that's just the same as 1, up there. So that's the same as 6x to the first. And why I did that is because I have to subtract my two exponents. So 4/4 minus 3/4, that's just 1/4. So I get 6x to the 1/4. And then I did, go ahead and I graphed these. to kind of verify. What I do see is that I'm fourth rooting, and we can't take the fourth root of a negative number, very much like we can't take the square root of a negative number. So the domains are actually the same as they were in example 1. And again, your calculator will verify that. The next little bit we have is an activity that we're going to do as a warm-up. When you come in during our next lesson, you're going to take some time to sort of summarize what you learned from the past few minutes ago, just about how do you add, subtract, multiply, and divide functions, and then you could talk about the domain. So we'll talk a little bit more about that when you get to our next class. The next thing I wanted you to start to think about, and if you could press pause right now, that would be beneficial to you. I just wanted you to do a couple of review questions before you went on to see the answers there. So take a second and press pause. I'll do the same. Okay, so I just wanted you to kind of get a little bit of practice with your function notation. In part A, you just had to plug -3 in to f of x. Tricky part there is when you square that -3. If you got this one wrong and you didn't get 34, if you square that -3, you have to remember that that is going to be a positive 9. So just watch yourself with that. When you add the two functions together, a little bit of practice from a few minutes ago, you should have gotten 2x squared minus 8x plus 8. And it doesn't really matter about the order, does it? G plus f of x is the same of g of x plus f of x. So you get 2x squared minus 8x plus 8. The order did not matter for addition. Oh yeah, but it sure did for subtraction. You did not get the same answer. So order does matter with subtraction. We could say that subtraction is not commutative. So those are your answers for D and E. And then I wanted you to plug in 2 for function f there and multiply for function g. So that's a little bit of a warm-up for you. Okay, so a little bit about prior knowledge. Remember, you could have some, let's say we have a real simple linear function like f of x equals -2x plus 5. You could plug things in to functions for sure. You could plug in, you just did it a few seconds ago. You could plug -2 in for x wherever you see it. So anytime you see an x, you could put in a -2. You know that. You were able to do it in the warm-up just a few seconds ago. The idea that we could substitute things in for x isn't new, but we can substitute other things in besides just numbers. We can substitute in, let's say, other stuff. So for instance, like what if I wanted to plug in maybe 3y? What do you think f of 3y would be? Why don't you take a second and play around with it and press pause again. And if you plugged in 3y, it would look like that. You get -6y plus 5 when you are all done. So we get this idea that, you could plug in to a function using your property of substitution. You could plug in constants. You could plug in terms, other terms or other factors, depending on how you look at it. And you could honestly plug in some bigger stuff too, and that's kind of what we're getting at today. How can we plug other functions into an original function? So let's do something bigger. Like this time around, let's say, I'm going to plug in 5a plus 1 instead. So instead of plugging in 3y, like you did up here, wherever you see x, you would plug in 5a plus 1. Ultimately, you would get -2 times the quantity of 5a plus 1 plus 5. And then you could simplify that by using your distributive property, and it would simplify to be -10a plus 3. So did you get that? If you did it, you're getting the hang of it. That's pretty good. Pretty good. So make it a little tougher. So this is our new information. I don't want to overwhelm you there with too much. This is our new bit, real brand new bit. You might recall you were substituting 3y or 5a plus 1 in there. All you were really doing was plugging one function into another. And when we do that, that's really what we call function composition. It's the same as substituting in it, just a regular number. Just we can plug in another equation. So let's take two equations, like f of x equals 4x plus 9 and g of x equals negative 5x minus 2. We can do some composition of functions with that. Let's say we want to know what happens when I substitute g of x into f of x. If we substitute g of x into f of x, we call that f of g of x. I know, doesn't that look weird? Some books actually write it slightly differently. Instead of doing the little g of x inside f of x, they do like a little fog, F-O-G. It's not really an O, it's actually a really small little circle of x. So some books will write it like that also. But regardless, what happens when they do that is you'll see that they take f of x and they kind of open it up. And you know, you see here x is right next to the 4 in f of x. So what we do is we take our function g of x right there and you plug it in where you see the x in f of x. So you just substitute that equation into f of x and then you simplify. So it's pretty simple. So this simplifies to be, if I distribute the 4 in there, negative 20x minus 9, or minus 8 and then plus 9. Can you spot the g of x inside the f of x there? You see it? Yes. And then we simplify. And then we have another example to show you. So we have our two functions now still. F of x is 4x plus 9 and g of x is negative 5x plus 2. What if we wanted to do it in reverse? You know, let's do g of f of x this time, such that you could open up function g. So, whoops. Try that again. Open up function g. There we go. And open up function g and then plug in f of x where you see it. Here's how I typically do that. I write my function out. Oops. Buggy today. There we go. So I open up my function, you know. G of x was negative 5x minus 2 up here. So negative 5x minus 2. That's my g of x up there. And then wherever I see the x, kind of just leave that blank. And then I take my 4x plus 9 right here, and I plug it in to g of x. And then I can just distribute and simplify. So do you see how I just took my function right here and I plugged it in to function g? Well, bam, just right in there, right where the x was. So I have negative 5 times the quantity of 4x plus 9 minus 2. And then we distribute, combine our like terms, and you get negative 20x minus 47. And if you simplified it, that's what you got. See? Great job. And I just wanted you to get a little bit of practice, so you can go ahead and pause. Give yourself a little bit of practice. I'll do the same. I'll show you your answers there. And this is the end of the notes that I needed you to copy down. So 20 minutes there, not too bad. Yeah, so you'll see right below this end of self-guided notes that I do have more examples to do with you. So if for some reason the self-guided notes weren't super helpful, we're going to kind of walk around and help you out a little bit when you come back to class for our next lesson. So we'll do a little bit more with this, and we'll get some more practice with this the next time I see you. All right, take care.